Okay, so anyways, I hope everybody's having a good day. A few things. This is the first lesson where I don't have copies of the homework to go ahead and give to you. It's going to be due on Thursday, but this is the first time you're going to have to go to the website, either print it off, copy the problems, whatever you want to do. Okay. Unfortunately, I'm not able to copy those anymore. So if you go to our website here, okay, you'll notice I've already started posting the focus activities. But if you go to the current week, 10:7 to 10:11, we're currently on the lesson arc length and circular motion. You click on it, here are the notes we're talking about. Then you always have the filled in notes. And then at the very end, that's where you have your homework assignment. Okay, so this is going to be due on Thursday. Now it becomes even more important. We got a test coming up over this same material. But also, if you want to retake quizzes and tests, you have to have the assignment done. Okay, so there's a little more responsibility on your part. So if you have any trouble, please let me know. But please also take care of that. All right, so we got the exit ticket out of the way. What say we go on to our focus activity? Bless you. This is number 3. All right, these are going to be due on Friday. You'll have 4 of them, and Mr. Yacht is going to work the 4th one with you on Thursday. That's at least the plan as of right now. So it says a graph of a step function is shown below. Which key attributes describe the step function? So really, you're just looking at these 4 statements here, trying to figure out which ones are true and false, and then using that to pick your answer, F, G, H, or J. Does anybody believe they know what the final answer is? F, G, H, or J? Philip, what do you think? J. It is not J. No, sir. Okay, Sandra, what do you think? It is not G. Okay, Will. It is F. There we go. All right. So let's go ahead and talk about that. Let's talk about it. Let's just start with the first one and work our way down. It says the function is symmetric to the origin. Okay, is that true? It is not true. Now, graphically, that means I can go ahead and rotate it 180 degrees, and I should end up with the same graph. It's kind of hard to visualize that here, so let's think about it algebraically. Any point on a graph AB, if it's symmetrical with respect to the origin, should become negative A, negative B. Okay. Now, that does work for a lot of these points on here, specifically the ones that are the closed circles. That works very well for them. But if we go ahead and take, say, a point off of one of these steps right here, like this guy would be 1/2, 0. Well, according to this model, what would become of 1/2, 0? It would be negative 1/2, 0. But if I go ahead and plot that point, the graph does not exist there. Okay, so this guy is not symmetric with the origin. All right, so 1's out. So that also eliminates H. Okay, 2, the function is decreasing. What do we think, yes or no? Okay, well, we already know what the answer is, so we can go ahead and say, no, it's not decreasing. But can anybody tell me why? I mean, overall, it looks like it's dropping to the right. Will, what do you think?
I mean, within each of the intervals, it's constant.
That's exactly right. The definition of decreasing, as x gets larger, the y values decrease. But if you look at these intervals, the steps, just choose one of them. As the x gets larger, the y values are remaining constant. Okay, so we can't say that's decreasing. Okay, so that one's out. All right, so any answer with 2 is also eliminated. So now we at least have it to F and J. 3 says the domain of the function is, now remember, this is a solution set. All values of x, what's that bar mean?
So,
Okay, such that, okay, x belongs to the real numbers. Well, is the domain of this guy all reals? Okay, I'm thinking yes. But I'm looking at this and I'm seeing a lot of open circles. There you go. The other step kind of accounts for that. Even though this step doesn't include 1, this step does. Okay, so 3 is good. But unfortunately, that doesn't help me narrow it down between F and J. So now we come to 4. The range of the function is all y such that y belongs to the reals. So is the range, the height, all reals? It is not. In fact, take a look. If you're looking horizontally, there are values of y that don't exist. There are gaps, like negative 1/2, 1/3, anything in between these values. So basically we have 0, -1, -2, -3, continues. Then we have 1, 2, 3, continues. What set am I describing? Starts with an I. The integers. So the range here would simply be the set of integers, not the real numbers. Okay, so F is the only answer. Okay. Now there's kind of good news and bad news. You remember next week, Thursday and Friday, is when we're going to be taking our 9-week assessment. Okay. The good news about this is, well, I don't know if I'd say it's good news. They did exactly what I thought they were going to do. They increased the number of questions to 24. But I was looking at the district assessment yesterday. All they did from previous years, they took the district assessment we gave in the first 6 weeks and the second 6 weeks, and they took problems straight off of them. Okay, there's like no variation. So what I've done in past years, every problem on the district assessment that was the most missed, like this one, I turned it into a focus activity so we'd have the opportunity to talk about it. But this problem does appear where? On the 9 weeks assessment. That's what these current focus activities are covering. Problems that were missed from those. Okay, so probably a good idea, at the very least, if we're still not understanding it, definitely go ahead and remember the answer, because I believe the fourth focus activity is on there as well. I'd have to double check that. Okay, but you know, the only reason I bring that up is because remember the 9 weeks assessment does not count for a grade. It does not affect your average in any way, but it will appear where? It will appear on your report card. Okay, the next time we get a report card. So you still want to do the best you can over the 2 days that we take it, because otherwise you're going to find yourself in a situation trying to explain to your folks what this low grade means on your report card. And I don't want anybody to have to do that. Okay, the good news is everything on that assessment we have talked about since the beginning of school. Rationals, just functions in general, all kinds of things. Okay, well, let's go ahead and put that somewhere safe. Homework, right triangle trig. Okay, do we have any questions about the assignment that was due today? Hey, press up. These last questions, okay. No, because it says do this without a calculator. And actually, this is really, really important moving forward, especially after we talk about the unit circle. You need to be able to evaluate these without a calculator, whether I give you the degree or I give you the ratio. So let's kind of talk about one of these, 19. I'm given sine of theta equals the square root of 3/2. Okay, so I want to figure out what the value of theta is without just plugging it in the calculator. All right, so I'm going to create a right triangle. Now, it does not matter where I place theta. Would you like me to place him above or below? What's that? Below. So I'm going to put theta right here. Now, once you choose which angle is theta, then the sides are going to be very specific. Remember, sine is always opposite over what? The hypotenuse, right? So because I placed theta here, the side opposite that would be the square root of 3. The hypotenuse would be 2. Now, whether you recognize it or you use the Pythagorean theorem, can anybody give me the third side? It is 1. Does anybody recognize what type of triangle this is? It is a 30, 60, 90. We are going to be using these special right triangles for a long time when it comes to the unit circle. This is what your happy minutes are going to be like eventually. Okay? So I'm going to have you find angle measures, I'm going to have you find ratios, all kinds of different things. So the only question is, which one's which? Now this top one right here, would that be 30 or 60? Okay. Not 60. Why would this one here be 30? How would we know? Remember, the smallest angle is always across from the shortest side. One's the shortest length. So if this one's the 30, then the angle I'm looking for has to be 60. Okay, so that's how you'd want to do these without the calculator. So because we know we're dealing with special right triangles, that means the rest of these, if it's not a 30, 60, 90, it would have to be a what? It would have to be a 45, 45, 90. So again, being able to recognize those types of triangles is going to be very, very important to you. Okay, the more comfortable you feel with it, the faster you're going to get. All right. So is that good? Did anybody have any other questions? 15? Okay. So let's see here. Solve for the variable shown. Now this one, we are going to have a calculator help me out. So I've got an angle that's 32 degrees. So what would the 15 and the x be to that 32? 15 is the what? Opposite. What's the x? The hypotenuse. Okay. So what trig function uses an opposite and a hypotenuse? Sine. But we can also use what? Cosecant. Remember, those are reciprocals of each other. We need to know all 6 of those trig functions. So I could say the sine of 32 degrees equals the opposite 15 over the hypotenuse x. Or I could use the cosecant of 32 degrees equals the hypotenuse x over the opposite 15. Okay. Now, either one is going to give me the exact same answer, but typically people tend to want to use the trig function where your x, your unknown, is in the numerator. Because then all I have to do is what? All I have to do is just multiply through, and that's easy. You'll just have to do like one extra step if you have the sine equation. Okay. So in this case here, 15 cosecant of 32, I believe my calculator is in degrees. Let me go ahead and check that. Sine of 30 should give me 1/2. Okay, so I'm good. So what was this? Cosecant of, what was it, 32? And I was multiplying that by 15? Okay. So that hypotenuse should be 28.3 units. Okay. All right. There is one other thing I wanted to go ahead and bring up on the assignment, because again, it's really, really important to you. It's one of those things that can easily cost you points on, say, a quiz or a test. Look at numbers 9 through 14. Now, these are supposed to be very, very simple problems, guaranteed problems. All you have to do is just type it in the calculator, right? But why are these kind of dangerous? What's that? No, the number of decimal places is what's important. You'll notice, look at number 12. Am I giving you degree or radians? Okay, Will says radians. How do I know immediately that's radians? Pi. Pi is a huge red flag when you're talking about an angle measure. Okay, but you'll notice I've highlighted 13 and 14. 1.85 and 2.85, what are those? Those are radians as well. How do I know those are radians and not degrees? That's the trick. If it was truly meant to be degrees, then you would have the little degree symbol right here. Okay, so that's something very easy to miss, but very, very important. Okay, you can have a radian measure without pi. In fact, it's going to happen a lot. Okay, yes, ma'am. Yeah, you can either just change the settings in your calculator, or if you want to just keep the settings the same, you could take like 2.85, multiply it by 180 over pi, and then input that into your secant function. I mean, there's all kinds of ways, but it also makes things a little more dangerous because now you know people are changing the modes on your calculators. So whenever you're calculating these, you need to know, is your calculator in degrees or is it in radians? Because whatever mode it is, you might be inputting pi over 8, but it's thinking it's in degrees. Okay, so again, just something to be, very aware of. Okay, good. That's not what I needed. Show me those. Okay. Well, let's go ahead and start talking about linear and angular velocity with the time we have left. Okay, now just a quick recap. Yesterday, we spent our time talking about arc length, which had the formula S, the arc length, equals the radius r times theta in radians. But we also talked about area of a sector. Does anybody remember what that formula was? A equals what? 1/2 the radius squared times theta in radians. Okay, again, both these formulas have to have theta and radians. This is what we were looking at yesterday. Okay, well now we're going to expand our discussion to this guy right here, linear and angular velocity. Okay, so have you ever thought about math while out for a bicycle ride? Sure, we all have. You know how to find your average speed by calculating distance traveled divided by the time from long ago. So we all remember the DIRT formula, D equals RT, distance equals your rate times your time. All right, so if I wanted to know how fast I was going, I would take the distance and divide it by the time. Now in trigonometry, we're going to call this linear speed or linear velocity, and we rename the variables. So V is going to be our velocity. Bless you. S is going to be our arc length. This is the distance that we've traveled. Okay, and of course T is going to remain time. So you'll notice here I've kind of equated the two. D equals RT is also going to be used here as S equals VT, just with the concepts we're looking at here. All right, now if I want to go ahead and find the linear speed, our formula right now is to take the distance traveled, okay, that's my arc length, divided by the time it took. All right, now this will be changing in just a little bit because I'm going to introduce angular velocity. But let's try an example. Okay, dimensional analysis. If you travel in a car at 65 miles per hour, how far do you go in 10 seconds? Okay, so what are they asking me to solve for here? V, S, or T? The question says how far, so I'm going to be solving for S, my distance now. That's what S is. That's arc length. Now remember, all of these problems are going to be dealing with wheels of some type, some kind of circle. So, you know, as the wheel rotates, the arc length increases. That just means the distance increases. Everybody okay with that? Okay. So we are going to be using this formula here, S equals VT. All right. Well, we have the time T. All right. Now, we do have the speed, but I'm going to need the speed in miles per what? Miles per what? Seconds, because that relates to my time. If I'm going to truly find the distance, I need that time to cancel out. Okay, so I'm going to go ahead and start here. Okay, my velocity is equal to 65 miles in 1 hour. Okay, now what I want to go ahead and do is convert this to miles per second. I want to go ahead and get it the same time as what I'm provided here. So this is what we call dimensional analysis. I'm going to have to go ahead and put in one or several more ratios until I get the units that I want. Now, if you're already very familiar or comfortable with this, there are shortcuts where you can combine some of these. But in the beginning, I'm going to go ahead and write everything out because I don't want to lose anybody. So if I want to go from hours to seconds, I'm first going to go through what? What's going to be between seconds and hours? Minutes. Okay, so I'm going to go ahead and put the hours up top because I want that to cancel. And then I'm going to have minutes. Okay. So what's my ratio here? What am I going to put? Yeah, 1 hour is equivalent to 60 minutes times. Now I want to get rid of the minutes, and I ultimately want seconds. So what's it here? 1 minute, 60 seconds. Okay. So this is what we refer to as dimensional analysis. As I go through, my hours are going to cancel, the minutes are going to cancel, so whatever I calculate is going to be in miles per second. Okay, that's what we're wanting. So really all I have to do is take 65 and divide it by 3,600. Okay, so 65 divided by 3,600. All right. So let me go ahead and calculate that. So let's say 0.018. I'm going to go ahead and round it to write it down. Okay. So about 0.018 miles per second. Okay, so now I have the correct velocity. I've got the time, so I can go ahead and find the distance traveled in those 10 seconds. Okay, so the distance, that arc length, equals, well, the 0.018 miles per second times the 10 seconds. And there might still be some people out there wondering, why did we have to go ahead and convert that to seconds? Because my distance won't have time associated with it. So I needed the time to cancel. So all I'm going to have is what? Oh, not minutes. Miles. Okay. Now remember, I went ahead and rounded it to go ahead and write an answer down on the board, on my paper, but I'm actually going to go ahead and always use the calculator when I go ahead and do that. All I'm going to do is move the decimal place 1 point over. So let's say 0.181. Okay. There you go. So how far are you going to travel in 10 seconds? Well, 0.181 miles. Okay. So just shy of 1/5 of a mile. Okay, how we doing? So linear velocity is speed, but for the types of problems that we're going to be looking at, we're talking about speed in a circular path, because a lot of these items, they're going to be rotating or spinning at certain speeds. Like we could be talking about a vinyl record, a bicycle wheel, a DVD, I mean anything that fits the idea. Now this is angular speed. Let's look at another type. Think about how fast the wheels are rotating. This is called angular speed or angular velocity. The Greek letter omega, the curvy little w here, is the accepted variable. Remember, v is your linear speed, linear velocity. Omega, the lowercase letter, is going to be angular. Now, this is the rate that measures changes in the wheel's central angle over time. So how fast is that angle rotating with respect to time? That's what angular velocity is. Okay, it's not linear speed. Now, it's always going to be in radians per time. Now, because the wheel is spinning, you have the triangle here to indicate change, but we're just going to go ahead and say for right now, omega is going to be the central angle divided by time. Okay, just to kind of streamline things and make it go a little faster. All right, so let's try an example. If a central angle spins at 15 radians in 8 seconds, how fast is the angle spinning per second? Well, how fast is the angle spinning? That's asking you, what is the angular speed? What's the angular velocity? Okay, well, we have the time t. Okay, what do you think the 15 pi radians is? Yeah, that's my angle theta. That's how fast it's rotating with respect to time. Okay, so I'm just going to go ahead and apply this formula. So omega equals, we've got 15 pi radians per 8 seconds. Okay, remember, just like I have here, angular velocity is going to be shown in radians over time. Okay, yeah. I'm going to go ahead and calculate that, 15 pi over 8. So I'm going to come on over here. Let me clear this out. So control divide 15 pi over 8. Okay. There we go. So about 5.890, because I think it said round to the nearest thousand, didn't it?
Yes.
Okay. So 5.890 what? There you go. Radians per second. So that is almost a full revolution every second. Now I say almost. Can anybody tell me what's one full revolution in radians? It is 2 pi, right? But what would that be as a decimal? 6.28 radians. Because remember, pi is just 3.14, right? So if I double that, that's where I get the 6.28. So see, that's why I'm saying it's almost one full revolution per second. That's my angular velocity. How fast is the angle rotating with respect to time? Okay. Well, let's go ahead and kind of sum this up. Okay, linear and angular velocity. Remember, linear velocity is v. And the formula we have right now is the speed is equal to the distance divided by time. The arc length s divided by time. Okay, for angular velocity, we have that omega, Greek letter. We're saying omega is equal to the change in the angle with respect to time. Okay, so linear velocity has dimensions of length per unit of time. So we have feet per second, miles per hour, meters per minute. So some distance per unit of time. Now, angular velocity has dimensions of angle measure, radians, per unit of time. So revolutions per minute, radians per second, degrees per hour. So angular velocity is how fast it's spinning in how much time. Okay, the number of revolutions over the time. In fact, every time you think about angular velocity, I want you to immediately think of this right here. Okay, this little expression. the number of revolutions in how much time is given times 2 pi radians over 1 revolution. And remember a second ago I said that angular velocity is always, always, always going to be in radians per what? Second, so it's some kind of time, right? Radians per time. Well, do you notice anything about this expression? Anything going to cancel? The revolutions will cancel. As soon as you try to find angular velocity, the revolutions will cancel. You're going to be left with radians per time. Okay. Now, this first one is going to depend on the problem. How fast are you spinning and how much time are you given? But this second fraction right here, 99% of the time, you're going to be using it. Okay. Now, there's always that one chance you could be doing it in degrees, which is what 6b is going to have you do. Okay, so let's try some of these. Okay. Convert 60 RPMs, revolutions per minute, to radians per minute. Okay. So I want the angular velocity. So I always start with this fraction right here. How fast am I spinning? 60 revolutions. Okay, so that's the number of revolutions. So 60 revolutions in how much time? Per minute. So 1 minute. Okay, times. Now I'm going to go ahead and convert that to radians. So I'm going to multiply this by 2 pi radians in 1 revolution. Every single time you find angular velocity, the first thing that should cancel are your revolutions. So that now it's what? Radians per minute. Okay. Now the time again could be anything. Seconds, minutes, hours, milliseconds, anything you want it to be. All right, so typically the problem is going to tell you what you want. So how would I figure out how many radians per minute? Yeah, just multiply. What's 60 times 2 pi? Okay, so I would go ahead and say, this one doesn't say to approximate, so I'm just going to leave it as is. I'd say 120 pi radians per minute. So 120 pi radians per minute. Okay, let's try 6b. Now, this is the one time where you're going to start off the same, the number of revolutions over time, but you can't use 2 pi radians because this one wants what? Wants degrees. So don't say it out loud. Think about what ratio is going to give me the degree measure I'm looking for. Okay, so take a few seconds. I'm going to go ahead and start it out the same way. The number of revolutions in the time. So we're starting out again with 60 revolutions in 1 minute. And don't forget, tomorrow is our CFA quiz. That's the one we're going to be doing on the calculator. You'll have some scratch paper. I'm thinking like 12 minutes because I think we got 4 problems. It's multiple choice. It's not going to be horrible. Okay. At least I don't believe it should be. Or at least hope it isn't. Okay. All right. Can anybody tell me what I should put for that second fraction? There you go. Now see, if we want it in radians, we know 2 pi is 1 revolution in radians. But if I want it in degrees, 360 degrees is 1 revolution. Okay. Now here's the thing. My revolutions are going to cancel, just like they always do. But this is going to be in degrees per minute, and this problem wants what? Per second. So I need to go ahead and tack on 1 additional ratio to get rid of the minutes. Okay, so what should my ratio be? 1 minute is 60 seconds. Okay, so you'll notice the minutes now cancel. So I've got the degrees per second that I want. But do you notice anything else? Yeah, the 60s actually cancel this time as well. So we should just be getting 360 degrees per second. How many people got that right? Okay. How many people set it up correctly but didn't notice that it was per second? They left it as per minute. Okay, so that's just something, you know, we'll look at. Okay. All right. Now here's a little derivation for us, because I said the linear velocity problem was going to be changing. Okay, the formula. Right now we have the formula is equal to linear velocity equals the distance divided by time. We also have the angular velocity formula, which is the change in the central angle divided by time. Everybody's okay with that? Any questions? Now, again, we know that the wheel is rotating, which is why we have the triangle here to represent change. So kind of just disregard that for a second. Okay? So I've got V is equal to S divided by T, right? Well, now I've got V equals R theta divided by T. What'd they do? Like, how do we know that S equals R times theta? The formula for what? Arc length. Remember, that's what we were talking about yesterday. We had S is equal to R theta. So all I did was replace this S with the R theta. Okay. Then in the next step, you pull the R out. Well, you've got theta divided by T. Does theta over T look familiar? That's your angular velocity. That's omega. So all I did was replace theta over T with omega. This is the formula we're now going to be using for linear velocity. This is why every single time I solve an angular or a linear velocity problem, even if it doesn't ask me for angular velocity, I always find angular velocity first. As soon as you multiply that by the radius, you have linear velocity because you've introduced a unit of length. Okay. So let's try an example. I think we got enough time to get away with this. So these are the problems that I texted about yesterday and that I went ahead and told you about in class. So like I said, you'll have a short time to copy, not a lot, because right now it's already 46. Okay. So if you have copies or if you wrote it down, I mean, you know where we're going tomorrow, so probably not a bad idea to take a few minutes to do something about that tonight. Okay. But number one, it says a typical vinyl record has a diameter of 30 centimeters. When played on a turntable, the record spins at 33 1/3 revolutions per minute. A, find the angular speed in radians per minute of a record as it plays. Round to the nearest tenth. Now remember, what we're going to go ahead and do here, okay, formula to find that, okay, was theta divided by T, but if you set it up as this ratio, it works out every time. The number of revolutions with respect to time. See, that's your theta divided by T, but we want it in radians. So I'm going to multiply it by 2 pi radians over 1 revolution. Okay. This is how you're going to start like 99% of these angular velocity problems. Okay. So in this problem right here, how fast is the vinyl record spinning? (33 1/3 revolutions in how much time? 1 minute. So that information helps me create the first one here. So for A, and because it's a mixed number, I know this would be 33.3 repeating. I'm just going to go ahead and round it to 2 decimal places. So I'm going to say 33.33 revolutions in 1 minute. Okay. Times, now I want to go ahead and make that radians. So I'm going to multiply by the 2 pi radians in 1 revolution. Okay. Now this first part here simply wanted radians per minute. Is that what I have, or do I need to do some more analysis? What do you guys think? Yeah, I have it. The revolutions are going to cancel. There's radians per minute. So all I need to do is multiply 33.33 times what? 2 pi. So let's come on over here to the calculator. 33.33 times 2 pi. Remember, pi was down here at the bottom. Okay. So I'm getting my angular velocity. How fast is the angle rotating with respect to time? To be 209.4 radians per what? Okay, so this is 209.4 radians per minute. Okay. Now, here's the thing. Remember, this is my angular velocity. This is omega. In order to find the linear speed, the linear velocity, that's V is equal to R times omega. Well, what was R? What does R represent? The radius. Well, what's the radius of my vinyl record? 15. So here's the thing. If I want V for part B, I'm just going to go ahead and write it out because, again, I want you to see what we're going to do. I'm going to take the angular velocity, okay, the 33.33 revolutions in 1 minute times 2 pi radians in 1 revolution, okay. This right here gives me my angular velocity. As soon as I multiply that by the radius, it becomes my linear speed. So what I like to do, because I start with fractions anyway, I always go ahead and put the radius over 1, because you got to multiply across anyway. Okay. Now, when everything cancels, here's the thing. Revolutions are gone. Now, as soon as you introduce a unit of length, you no longer are worried about the radians, because you've given it something to measure. So the radians can disappear. This is now going to be in centimeters per what? Centimeters per minute. Is that what the question wanted? It wanted centimeters per second. Okay, so I do have to go ahead and add on another ratio here. But is everybody seeing how I'm doing this? You find angular velocity using those two fractions. In order to find linear velocity, you multiply angular by the radius. What should I put here at the end? I should put 1 minute over 60 seconds. See, there we go. Now the minutes are going to cancel. Now I've got centimeters per second. So I would take 33.33 times 2 pi times what? 15, and then divide that by 60. So if I actually put like a little dot on the vinyl record and I watch that dot spin around, this linear velocity would be telling me how fast it's actually traveling. Remember, it's going to be traveling in a circular path. Okay. All right, so remind me that we almost finished B tomorrow. We'll go ahead and start.